Let's go ahead and kick this thing off. Hello, welcome again to another CIRP technical discussion. Today we have Scott Spurgeon and Brooke Walker from our Next Gen Coastal Volumes project under the CIRP umbrella. And Scott and Brooke have been working on some space-time cube analysis and finally got our technical note through. So hopefully, right, that's the one that was recently published. Not the lit review. Yeah, so we have actual published material on that as well. Hopefully Scott will point to that, and if not, you can email him and he'll point you to it, or it should be on the CIRP website. It should also be on the CIRP website shortly. Mitch, please and thank you. You're the best. So yeah, excited to kind of wrap that piece of this project up this year. Coastal Volumes will be, we're in our final year for this project with some carry in into Q1 to wrap up a few things, make sure everything's working, and everyone has the appropriate access to it as well. So I will turn that over to Scott and Brooke.
Great, thanks, Marissa. Good afternoon, everybody. My name is Scott Spurgeon. I sit at CHL, but I sit down in the Kiln, Mississippi office with the iAtlas, which is the formerly JavaText group. And I'm going to be talking with Brooke Walker today about spacetime cube analysis using ESRI tools. This is, like Marissa mentioned, is a part of the larger Next Gen Volumes CIRP work unit. So just to give you some background for this CIRP project, it really applies for two statements of need, and we're addressing both. And the primary goal is to update the existing framework of volume change that uses these fixed in space bins to capture sediment transport methods. These bins are created from a transect-based methodology and utilize DEMs of difference to compute volume change within the bin area. The shoreline vectors, volume above and below mean high water, and the volume change statistics are the primary output of the existing toolbox. The limitations to the current toolbox is that these bins are fixed in space, and they really just kind of group individual sections of shoreline together without any particular focus on individual features or anything specific about that shoreline. So you can kind of see the individual bins there in the example photo on the right side. So the best way for us to update this methodology and really better inform sediment volume change analysis and sediment transport during planning, construction, and monitoring is through the combination of this multi-dimensional space-time mapping approach with geomorphic feature segmentation and extraction and evaluation of uncertainty. And again, our goal here is to improve both the characterization and the quantification of volumes for coastal projects to support the sediment budget development. And so today we're going to be really focusing on the multi-dimensional space-time mapping approaches in the bottom left, and that's where space-time cubes come in. But there are definitely other portions of this project that this ties into. So to give everybody a quick background on what space-time cubes are, if you're not familiar, they're geostatistical tools that allow for analysis in 3 dimensions. The first 2 dimensions are your typical X and Y coordinates that put things on a map and tell you where that information is on the Earth's surface. And then your kind of third dimension is actually time. So you're able to stack data sets on top of each other based off of their age. And so each X, Y, and Z point is defined as a bin within the spacetime cube, and you see kind of a bin time series there as a individual stack of data sets at a given pixel location versus a time slice is what we, in this particular context, are considering to be an individual raster or an individual data set. And so these, again, are geostatistical methods, and so that's the focus here. But so far our work has focused on the Mississippi Barrier Island system and building spacetime cubes to complete analysis within this area of interest. You can see The map here shows us how many overlapping datasets we have at any given location. We have up to 13 different datasets at any particular location. Obviously, the offshore areas may not have nearly as much overlap in certain areas based on the particular LiDAR coverage for that dataset, but the onshore areas are much more temporally dense. And so we published a technical note that Marissa mentioned that overviews an ArcGIS Pro-based workflow and discusses best practices when utilizing elevation data specifically within that workflow. We've also investigated the existing ArcGIS Pro tools, and we'll discuss those today. But if you're interested in building your own spacetime cubes, I think ESRI provides a really straightforward, non-coding base to get started with spacetime cubes, and everything is kind of in that ArcGIS Pro interface and GUI. So if you're interested in that overview, definitely check out that tech note. This is an overview of the spacetime cube creation workflow. This is just one of the figures from the tech note. The spacetime cubes allow for statistical analysis, as I mentioned before, to consider things like hotspot trend analysis over time or spatial pattern identification and time series forecasting. We'll talk today about the geoprocessing tools that we use to create, visualize, and analyze these spacetime cubes. And when we talk about these tools, and we talk about statistically significant findings, for many of these tools, that statistically significant is based off of the global cube statistics. Occasionally, it might be based off of a neighborhood statistic where the user defines a certain neighborhood size in terms of a number of meters or number of cells. And so as we just have to be careful about what significant really means for those results, because they may fall within a certain limit of detection window or another kind of noise window, and therefore they may be statistically significant, but they're really still part of the noise whenever we actually look at the raw magnitude value. And so that's just something to be aware of. So ESRI has two toolboxes that are made for analysis of spacetime cubes, the spacetime pattern mining and time series forecasting tools. Toolboxes, we'll discuss both of those toolboxes today, but most of the tools that we found were most applicable for elevation data in particular, and LiDAR-based data sets are found in the spacetime pattern mining spacetime pattern mining toolbox, which I'll hand off to Brooke to start to discuss.
Thanks, Scott. So I'm going to start y'all off with the space-time pattern mining tool sets. Next slide, please. We're going to get started with change point detection. So change point detection identifies when and where statistically significant shifts occur in elevation time series data, and it distinguishes between gradual geomorphic change and episodic event-driven change, which makes it particularly valuable for detecting storm impacts or monitoring beach nourishment effectiveness. And it also can help track sediment deposition in coastal or riverine environments. The most important parameter here on the slide is your detection sensitivity parameter, which is a critical decision point as values that are too high produce overfitting, which detects noise rather than any meaningful geomorphic events. And values that are too low may miss real elevation shifts. So a general rule of thumb is that for every location, if it returns 5 or more change points, you should increase your sensitivity. The tool performs most reliably with the temporal resolution of 10 to 15 time steps. And you should always compare your runs between either the mean change type and the standard deviation change type in order to get a better or more complete picture of the changes detected. If you could, next slide, please, Scott. Okay, so here we have some visual observation of the results from the change point detection. And this is Dolphin Island down in the Mississippi Berry Islands. So change points are detected across the entire island, but with notable spatial clustering patterns. So we see that darker clustering along the northern bay shoreline and the most eastern portion of the island. And then in the mean change point detection, you can clearly detect the changes between the infrastructure elevation, which the standard deviation does not show. So mean captures the absolute elevation shifts, while standard deviation captures changes in elevation variability and roughness. So we can see that the mean change point accounts for all of that infrastructure that may or may not be changing following storm events in the space-time cube. And then the standard deviation is just capturing that elevation variability, so not the actual elevation shifts. Next slide, please. And here is a even closer look at the change point detection results. So this is the far western end, the western spit of Dolphin Island. And this is the mean, standard deviation, and the slope change point detection in comparison. So the mean analysis shows a change count for each bin where the elevation shifted, either increasing or decreasing overall. Standard deviation shows a change count for each bin where the elevation change shifted in its predictability. And the slope change point analysis shows the change counts of where the elevation shifted from increasing to decreasing. For the western end of Dolphin Island, the high number of mean and standard deviation change points could be attributed to actual changes, particularly the high value clusters along the Gulf side beach in the mean change analysis. However, many of the high change point clusters are also on the base side within that captured bathymetry. And these could be actual changes, but it could also be data artifacts showing up. And we have to individually compare the raster values of those change points through time to determine if those are accurate reflections of elevation change points. The slope change point detection analysis results highlight that the western spit of Dolphin Island has not maintained a consistent erosional or accretional trend, as most of the spit has experienced at least one shift in the sedimentation trend. Next slide, please. And I'm going to hand it over to Scott for emerging hotspot analysis.
Thanks, Brooke. The next tool within this toolbox is the emerging hotspot analysis. This was really the tool that I think we investigated the most, as it just had the closest correlation with kind of existing analysis methods. And whenever we talk about coastal data sets, a lot of times we're interested in hotspots, and that's just kind of a natural result. And so this was kind of the one that I probably poured the most time into. And it identifies locations within a space-time cube that show statistically significant trends in the value over time and classifies them accordingly. And so the detection of areas within with statistically significant accretion or erosion patterns is the primary application when utilizing elevation data. But I think there's some really important best practices and caveats that we kind of found with this the more we played around with it. And so we'll jump into those. Basically, we started with the elevation rasters themselves and just built a space-time cube using just basic DEMs. And we found that emerging hotspot analysis results basically showed us that statistically significant low values are your bathy and your statistically significant high values are your dunes, which makes sense, but it doesn't really mean a whole lot to us. We know where our high values are and we know where our low values are. And so instead, what I did is I created a set of difference rasters and used those difference rasters to inform the space-time cube instead of the actual elevation data. So instead, now a hotspot is going to be a statistically significant area of accretion, and then a cold spot will be a statistically significant area of erosion. And so the results are a lot more meaningful there. However, since the space-time cube requires 10 different data sets at any particular location to be able to give a trend based on the statistical minimum, the difference rasters are limited. And so you can see on the left side, kind of on the zoom in plot, that we get the cold spots where we have bathy, but then on the right side, you don't really have data trending in that area very much. And that's because you don't have 10 different data sets that are actually out there in the bathy, because you're taking a least common area whenever you do a difference raster. If you subtract a time 2 raster from a time 1 raster, the result is going to be a least common area. And then you put all those into a space-time cube and you get a least common area of least common areas. And so it really does limit your spatial coverage based off of your data density and how much data you have at any particular location. So the way I solved that was I kind of cheated a little bit. I interpolated the rasters and then created difference rasters and used those. And so I understand that I'm essentially artificially densifying the data. And this does solve the 10 data set minimum problem because I'm effectively doubling the number of input data sets. But I also understand that the artificial densification essentially makes certain trends more likely to come up in a hotspot analysis like this. So I have to be really pretty careful whenever we're interpreting these results to say, is something like a consecutive cold spot where the last two time periods within the space-time cube show cold spot. Well, because it's interpolated, that really actually only means the last time period was a cold spot, right? And so it's something that we have to make sure that because we're essentially artificially densifying that data, we have to be careful about the interpretation of results. That being said, while the densification of the data is artificial in this case, the space-time cube was able to generate significantly more coverage area as that 10 data set minimum was being met for a much greater number of bin time series. You can see on the left side there, kind of the limited area across Ship Island is basically that East Ship and West Ship portions, and that entire Camille Cut or Katrina Cut area is just not being included in the analysis, versus whenever we do the interpolated difference rasters, you start to get a lot more in there. Again, I think caution has to be taken when you're doing that, because that trend analysis may be a little bit overfit to the data whenever we do interpolation. But I think what this shows is that as we get more and more real LiDAR data sets, and we're able to get closer and closer to instead of a 10 data set minimum, but we're able to get to 15 or 20 or 30 data sets just over time, it'll make it so that we don't have to do nearly as much interpolation. We're able to hit that 10 data set minimum, and we're able to see real trends in this data and be able to understand where our hotspots and cold spots are within these areas. And so with that, I'm going to hand off to Brooke again here real quick to discuss local outlier analysis and time series clustering.
Thanks, Scott. Local outlier analysis identifies locations where elevation values are statistically anomalous relative to their neighbors in both space and time. And it uses the local outlier factor to compare the density of values in each location's neighborhood against the density of its surrounding neighbors' neighborhoods. The tool can be used to detect geomorphic anomalies such as locations eroding or accreting out of step with surrounding areas, and helping to detect data quality issues before an even more intensive analysis. The key input parameters are listed here on the slide, and each of those controls a different aspect of how the neighborhood comparison is constructed. The tool is sensitive to irregular temporal bends and inconsistent spatial aggregation, and running the tool with multiple spatial neighborhood sizes helps assess sensitivity and determine the correct neighborhood distance. Next slide, please. All right, so here we have some results. Again, we're at the western end of Dolphin Island, and I don't have a full zoomed out image of Dolphin Island because the the symbology goes completely grayscale and it's very hard to see. So we have a zoomed in portion of the western end of Dolphin Island. On the left here, we have primarily low clustering, meaning that the western end of Dolphin Island has consistently low elevation values surrounded by primarily other low elevation values. There is some high clustering towards the central spine of the island, and this is likely showing a more uniform elevation surface through time. And the western spit is dominated by never significant bends, which just means that each bend stays or maintains the same elevation range as its neighbors through time. As we move easterly towards the eastern end, but not all the way to the more populated end of Dolphin Island, the outlier analysis does appear to show a more organized high outlier clustering. And this could be attributed to infrastructure or vegetative ridges. And Scott, if you will hit down, the down arrow. I tried something fancy, but I don't know if it'll work. Yeah, okay. So if we bring up this just base imagery, we can see how those light red marks line up with the housing and some of the road and even some of those vegetative ridges there on the eastern end. And if we hit it one more time, Scott. So we go back to it. So we can see how we also see those multiple types outliers are also clustering on the eastern end, and that's just along that shoreline. And so this potentially highlights that highly dynamic nature of the beach zone because it's cycling through those high and low values repeatedly. And again, we see a lot of the never significant outlier types, which could again be due to how dynamic the island is. It's always changing, and so the patterns are harder to detect. So the local outlier analysis distinguishes between low-lying overwash flats or low clusters and elevated dune berm features high clusters. And so this tool, with the appropriate data, this tool can be sensitive to both natural and human-influenced elevation anomalies. Next slide, please. And so now we're going to move into the time series clustering. which identifies locations within a space-time cube that exhibit similar temporal patterns and groups them into distinct clusters, making it valuable for detecting erosion behaviors, seasonal elevation changes, and sediment deposition patterns. Again, we've got the key parameters listed here, but I wanted to highlight the characteristic of interest parameter, as this is the methodology of analysis. So you have 3 characteristics of interest: the value, the correlation, and the Fourier. Value clustering groups locations by similar elevation magnitudes. Correlation clusters groups on an increase or decrease proportionally over the same time. And Fourier profile clustering groups locations that share similar seasonal or periodic patterns over time. Like most of these tools, this one is very sensitive to bare earth data only. It has to have bare earth data. So the inclusion of vegetation or structures will produce cluster assignments that reflect surface cover rather than true geomorphic behavior. Next slide, please. Okay, so here is a comparison of the time series clustering by value versus the time series clustering by Fourier profile. The value parameter clustering resolves into 3 distinct spatial groups across Dolphin Island. It separates the bay side and western spit, while the Gulf shoreline and the island spine, and then the eastern developed portion in green. So you have the blue, the red, and the green. While the Fourier parameter clusters only by 2 types, or 2 groups, so you have your entire eastern end, and then your bay side, northern side of Dolphin Island, and then a very slender stretch along the Gulf Beach. All of that is in blue, and then you have that central spine in red. So the reduction from 3 value clusters to 2 Fourier clusters reveals that the eastern developed end of the island has a distinctly different elevation history from the low-lying bayside, and it shares the same underlying periodic and seasonal forcing pattern, suggesting that the development, the infrastructure on the eastern end has altered the elevation response, but is not a fundamental driver of those physical changes. The spatial shift in the red cluster between value and Fourier clustering is a diagnostically valuable result. It reveals that the Gulf Beach face and island spine are geomorphically distinct, while value analysis groups locations by shared elevation trajectories and provides a useful, general look at the geomorphic history of the study area. The Fourier profile offers a potentially more physically meaningful perspective by identifying locations that share those periodic and seasonal patterns of elevation change. And we are going to now move into time series forecasting, and I'm going to hand it over to Scott.
Thanks, Brooke. So the time series forecasting toolbox, we're just going to overview the toolbox real quick because I think there's some important caveats here. There's various tools within this toolbox, but basically you kind of pick which way you want to forecast your data depending on your data type. So they have a forest-based, a curve fit, and an exponential smoothing. And then you can evaluate those forecasts by location, depending on if you want to kind of do all 3 and compare, you can evaluate forecast by location. But basically the forecasting toolbox tool sets on the whole have some, I consider, some significant limitations in that there's a requirement to hold back at least 20% of the data sets for validation and verification of the forecast. And so unless you have a really large stack of data sets, which in this case we don't necessarily have a huge stack, there's not really an ability to actually forecast forward. It really just forecasts within the space-time cube timing. So you can see here on the right side, there's some curve fit forecast example results. It's forecasting for 2009, even though in this particular case, we have data from 1998 all the way through 2022 in this space-time cube. It's forecasting into 2009 just because it could only forecast so many data sets. And so many of these forecast types, including the curve fit you see there, don't really accurately predict elevation values. I think it's always important to realize that any sort of forecast like this, whether it's a curve fit or exponential smoothing, or even a forest base, they're not informed by coastal engineering understanding or geomorphology or any of those forcings that's actually happening out there. So you see in the curve fit example results in that kind of zoomed in plot out in the bathy, it's projecting a random land mass is going to appear. in 2009, and we know that that didn't happen. And so when you look at the RMSE values and how inaccurate that is, the RMSE jumps up a ton for those areas because it's just really unsure. And again, I think that's because in this particular case, fitting a curve to a lot of these elevation trends isn't necessarily the most the most accurate way to try and forecast elevation values. In this case, the blue highlighted cells indicate where the forecasting was parabolic. And so that's pretty much all of that kind of offshore area where the values are being projected as land all of a sudden. And I think it's because we just understand natively that, okay, elevations are not going to just magically become parabolic in nature. They're going to be a lot more variable and seasonal and complex than that. And so that being said, I will jump into the forest-based forecasting because this was the type of forecasting that we felt like did the best out of the three. For elevation values, it utilizes a forest-based regression to predict future time slices within the space-time cube. It creates a bunch of different independent decision trees that all generate their own prediction, and those predictions are aggregated. A pretty straightforward forest-based analysis here. And so it utilizes kind of the back end that ArcGIS Pro is pretty used to using in that forest-based and boosted classification regression tools. And so if you're familiar with those, it's using the same exact math and algorithm, and it forecasts those future values based off of that regression. And so it is expected to do a lot better whenever you're looking at complex trends or seasonality or other non-mathematical functions. And that's exactly what we expect with elevation data sets. And so one thing to note here is that it utilizes, again, that forecast and validation model for given data, as so you have to exclude validation data sets, and you still have to hit that 10 data set minimum. And so again, you're relatively constrained to how far out you can actually predict and forecast. That being said, this forecasting type was the only one within the ESRI suite that allows for multiple scales to be selected when forecasting. So as I was talking earlier about the statistics, you can select a global statistic or maybe a neighborhood statistic. This is the same sort of idea, is that you can tell it, I want to forecast, and I want you to forecast based off of the entire global information around this entire individual location, or you can say, no, I actually want you to focus on a particular neighborhood and forecast based off of that. And so if you have a good understanding of your site and a good understanding of your particular coastal dynamics in your zone, you're able to kind of tweak that as necessary and probably get a much stronger results by using a neighborhood, because you understand that something happening 20 miles down the beach isn't going to affect this particular spot. You're able to kind of narrow it down a lot more. So to give you an example of what this looks like, on the left side is the forest-based forecast, and we see what to me looks like much more realistic elevation values. If you gave me that raster and told me that it was real elevation, I'd probably believe you. I might question why your coverage was so sparse out there in the middle of the island, because typically topo is very easy to get, but that's just the nature of this forecasting. But it did generate the most realistic value across all the forecast types. The RMSE spiked in the edge locations where more major changes have taken place historically. So where larger storm impacts or placements have occurred, that's going to have a much larger RMSE, because again, it's deviating from that kind of normal trajectory, versus the center of the island where the elevations are a lot more stable, showed a much lower RMSE error. So you're able to see that RMSE map on the right side using 3 validation steps. So with that, I'm going to hand back to Brooke for one last time to kind of give a summary and some best practices here.
Thanks, Scott. Okay, so our limitations and considerations. Our input data quality matters. Data input into spacetime cubes greatly affects the output statistics. So post-storm, post-nourishment, digital surface models or DEMs, and spatial resolution uncertainty all have downstream effects. The temporal data density effects. Data that is temporally dense is ideal. Utilizing irregularly spaced sparse data can limit many of these tools, and there is a minimum of 10 data sets. And with each additional layer of data, your statistics become more robust. So 10 to 15 is your absolute, or 10 is your absolute bare minimum. forecasting tools. While some forecasting tools are able to generate your realistic forecast values, none of the models are informed by coastal engineering understanding, and all the forecasting methods require very temporally dense data to be actionable. Next slide. So which of these tools should you use? We've actually already narrowed down a lot of these tools for you. So we've done a little bit of analysis on every single one of these toolboxes. Change point detection is going to be ideal for finding statistically significant changes from the norm. So post-storm, nourishment, or other events like those. The raw value and trend changes are detected within the change point detection analysis tool. Your emerging hotspot analysis is going to be ideal for detection of areas that are statistically significant or significantly increasing or decreasing in sedimentation. So you have your hot or cold spots when utilizing the difference rasters that Scott talked about earlier. Your local outlier analysis is ideal for detecting of the outliers from the geospatial local norm. And it's one of the few tools that utilizes that spatial neighborhood information to derive its results. And it works really well in pairing with that emergent hotspot analysis. And then your time series clustering, which is ideal for grouping areas that exhibit similar patterns over time, use cases with both elevation and difference rasters. And next slide, please. Okay, and so why did we do this? So we're going to connect it back to our next gen volume change work. We have modernized the geospatial volume change framework that leverages high resolution elevation datasets and advanced spatiotemporal analysis methods to expand the understanding of elevation change patterns and improve volume estimates. Thank you, Charlene, for that blurb. It's very well written. So the CIRP Next Gen Volume Change Analysis work has several large goals to improve not just the processing of high resolution elevation datasets for volume change analysis, but also to improve our understanding of the forcing patterns at work in our coastal systems, allowing for better management of our coastlines. Spacetime cubes, along with the tools mentioned today, provide the opportunity to understand coastal change, not just through before and after snapshots, but through a multifaceted lens of time, space, and location. Additionally, these tool sets have shown us how important data quality is to understanding morphological change. And this ties really nicely into the bias and uncertainty work that's being done by our ORISE peers, Shane Nichols-O'Neill and Charlene Sylvester, which will help us to recognize and correct artifacts in our high resolution data set, giving us an even clearer picture of patterns when we run these tool sets again. While these tool sets do not directly calculate volume change, they have the potential to help us understand volume change in a more comprehensive way, allowing for better and more informed decision making. And that is it for Scott and I.